This is my second lecture in module 5, that is model adequacy checking, and here is the content of this module. Various type of residuals, and in the previous class we talked about regular residuals, standardized residuals, studentized residuals, and today we will be talking about the press residuals, and also next we will be talking about several types of residual plots, like normal probability plot or plot of residuals against the fitted values y I hat, and in the next class maybe we will be talking about partial regression and partial residual plot. Okay. So, before I start talking about the Press residual, just I want to repeat once more the objective of this module. Here if you can recall in simple linear regression model or in the multiple linear regression model, we have assumed that the error term, the epsilon, has 0 mean, and the error term epsilon has a constant variance, and the error terms are uncorrelated, and they are normally distributed. So, what we are going to do in this module is that we will present several methods to check the underlying assumptions we made on the error term epsilon. Okay. And the methods are they mostly primarily depend on the study of residuals, because we think it is convenient to think that the residuals are the realized or observed value of the epsilon. Since we are going to test some assumption on the error term epsilon, so the test for that is based on the residuals, and the graphical analysis of the residuals are very effective to test the underlying assumptions on epsilon. Okay. So, now I will be talking about Press residual, which is one scaled residual. So, I have already talked about regular residual and the other things. Today I will be talking about Press residual. So, it is a beautiful concept here. The ith Press residual it is denoted by E bracket I is equal to y I minus y I hat. Okay. So, we know that y I is the ith observed value, and what is y I hat, where y I hat bracket I is the fitted value of ith response based on all observations except ith 1. Okay, so the basic logic behind this is that, so this is not the regular residual, this is the ith observation, the response value of the response variable, and this is the fitted value of the ith response based on all observations except the ith observation. Okay. Let me just give some idea about this special type of residual. I will just refer the previous example. This is an example of influential observation. Now, if I fit a model based on all the observations here, including this influential observation also, my fitted model may get influenced by this influential observation. Okay. So, my fitted model may look like this. So, this is the fitted model because of this influential observation, and you can see that the fitted model has been influenced by this influential observation, and the fitted value here, I mean this is the model based on all the observations. So, the fitted value here is y I hat. So, this is my y I hat, and this is I am considering this as the ith observation, for example, and this is my y I, this is my y I. Suppose this is ith observation, then the residual, I mean the true value of the ith observation, that is the true value y I and the y I hat, they are the difference is less. So, the difference is this much, and this is the ith regular residual E I. Now, if this ith observation is deleted from this data set, suppose this observation is not there in the model, in the set of observations, then my fitted model will look like this, and this fitted model is of course, it is not influenced by this influential observation, because I have I am fitting this model based on all the observations except this ith observation. Okay. So, this is what I am talking, this value is, that this value is y I hat bracket. So, this is what I mean, the fitted value of the ith response variable based on all the observations except the ith observation. Now, my residual, the revised residual, which I call here E I bracket, is this difference. So, E I bracket is equal to y I. So, this is my y I, right. So, this is my y I and this is my y I hat bracket here. So, y I minus y I bracket hat, and you can see that the ith Press residual is substantially larger than the regular EI. Okay. Well, so what we do is that we delete ith observation, fit the regression model to the remaining n minus 1 observations and predict yi. Okay. So, it may appear that to compute the first Press residual, that is E1 in bracket, you need to fit a model based on all the observations except the first observation. So, that is how you will get E1 bracket, that means the first Press residual. Again, you do not know which one is the influential observation. So, you have to repeat this process n times. So, to get E2 bracket, I mean the second Press residual, again you have to fit a model to the based on all the observations except the second observations. That means, you need to fit model based on n minus 1 observations that you have to repeat n times. So, but what we are going to do, I mean it can be it can be proved that you do not need to repeat this process n times to get the n Press residuals. It can be done based on one regression fit based on all the observations. So, here is the technique. However, so it says that it is possible to calculate Press residual from the result of one single fit to all n observations. Okay. It can be proved that EI, the ith Press residual, is equal to EI by 1 minus HII. Just recall that that this EI is the regular residual, and HII is the ith diagonal element of the hat matrix, and this is how this quantity and this quantity they are same. Okay. So, this is how we calculate the Press residuals E1, E2 up to En. Now, let me just recall the example we considered in the last class. So, here is an example of multiple linear regression with two regressors x 1 and x 2, and here is the response variable y, and we suspect that, I mean, it is likely that the ninth observation is an influential observation, or at least it is a leverage point, because x 1 coordinate is much larger compared to the center of x 1, and similarly x 2 value is much larger. And here is the regular residual, this is standardized residual, this is the studentized residual, and this is the praised residual. Okay. Now, here we check that for the ninth observation, the value of the regular residual is 7.41, whereas the value of the ninth praised residual. So, this is nothing but this is equal to E9 praised residual. This is 14.788, whereas the regular residual is 7.4. Okay. So, for the point for the ninth observation, the praised residual value is substantially larger than the regular residual. Okay. Now, also you can observe that for the 22nd observation, the value of the regular residual is 3.6, whereas the value of the praised residual is minus 6.05. So, here also the value of the praised residual is substantially larger than the value of the regular residual for 22nd observation. Okay. So, this is what regarding the praised residual, it appears that if the ith observation is an influential observation, or if it is a leverage point, then there will be substantial difference between the regular residual value and the praised residual value for that particular observation. Okay. So, next we move to residual plots. So, there are several residual plots we will be talking about. The first one is a normal probability plot. Okay. So, residual plots. Okay. So, first we will be talking about normal probability plot. So, before I talk about this residual plot, I just want to mention again that the objective of this module is to check the underlying assumption on epsilon on the error term. Okay. So, we will be talking about different methods to check the underlying assumptions. So, this is one of them. So, what this normal probability plot does is that basically check the assumption is that the epsilon I follows normal 0 sigma square and they are independent and identically distributed. So, this normal probability plot, what it does is that it checks whether the error term really follow normal distribution or not. So, here is the technique to test that. So, what it does is that let E1, E2, En be n residuals, that means the regular residuals. Okay. Let E box 1, E box 2, E box n be the residuals ranked in increasing order. Okay. So, given a set of data, you can fit the model, whether it is simple linear regression or multiple linear regression, and then you can get the residual values. You just rank them, I mean you arrange them in increasing order. Then what this normal probability plot does is that it plots E I against the cumulative probability P I, which is equal to I minus half by n, and you do it for all I is from 1 to n. Okay, so, very simple technique. You get the residuals first, you arrange them in increasing order, and then you plot E I against P I. Here is the P I minus half by n. Okay, so, just now I have different types of normal probability plots that may happen. This is so figure 1 shows the ideal situation. Here you can see that all the points lie on a straight line. Okay. So, if in your case, if you find that your plot when all the points are on a straight line, then you can assume that the error distribution is normal. Now, if here in the figure B, you can see that it is not really, I mean the points are not on a single straight line, and here if this type of situation occurs, then we can say that the distribution is heavily tailed. Okay. That is, it is not really true that the error distribution is normal. and figure C indicates that the distribution of the error term is lightly tailed. Okay. So, there is little deviation from the I mean it is not reasonable to assume if such situation occur, then it is not not advisable to assume that the error distribution is normal. Okay. So, this is what regarding the residual plot. So, residual plot basically it tests the normality assumption of the error terms epsilons. Okay. So, next we will be talking about one more plot, that is it's a plot of residual term against the fitted observation. Okay. So, here is the plot, a plot of residual E I against the fitted value y I hat. Okay. So, given a set of data, you fit the model first, and then you can get the fitted value. Once you have the fitted value, you can compute the residual, and then you plot the residual against the fitted value. Well, now we need to understand, I mean if the plot, or if the pattern looks like this, what does it indicate? Okay. So, if the plot of residual against the fitted value looks like this one, then you can conclude that this is a good regression model, and the good regression model will produce a scatter in residuals that is roughly constant with y hat and centered about E equal to 0. Then I mean what I am trying to say here is that if all the residuals are contained in a horizontal band. So, here is the horizontal band here, you can see that all the points are contained inside this horizontal band. Then there are no obvious model defects. That means, if what I want to say here is that if all the residuals are contained in a horizontal band centered about E equal to 0, this is the line E equal to 0, okay, because the residual value could be this is 0, minus 1, minus 2, 1, 2, 3 like that. Some of the residuals are positive, some of them are negative. So, you have observed that before also. So, what I want to say is that if the residuals are contained in a horizontal band, then there is no obvious defect with the model. That means it's a good fit. So, this is the only situation we say that the fitted model is satisfactory. Okay. So, there is no problem with the fitted model. Now, look at the second case. This is this figure B. Indicates an outward opening funnel pattern. Okay. So, here you can see that this EI values increase, I mean EI increases with the value with YI hat. Okay. So, this is called the outward open funnel pattern. What does this indicate is that this indicates that the indicates non-constant variance of epsilon I. We assume the we have assumed that the variance of the epsilon is constant, that is sigma square, but if your residual, I mean if your plot which plot I mean the this plot particular like epsilon versus epsilon EI against YI hat, if the pattern is like outward open funnel, that indicates that the variance of epsilon I or the variance of epsilon increases as Y increases. So, this one is sort of this is the indication of a non-constant variance. So, you can't, if this occurs, it is not advisable to assume that the variance of epsilon is sigma square. Okay. So, next we talk about some more pattern. The next pattern is, okay, one more thing just I forgot to mention here. Here instead of outward open funnel, it could be inward open funnel also. That means it would be look like this. In that case also indicates that indicates that non-constant variance of epsilon. In that case, variance of epsilon decreases as Y increases. So, both the, I mean it could be outward open funnel or it could be inward open funnel. So, both the cases indicate that indicate the non-constant variance of epsilon. Okay. So, next we will be talking about one more I mean some more pattern, like this is one more pattern. Here this is the line E equal to 0 YI hat in this direction, and this is called double bow, and this one also indicates non-constant variance. That means variance of epsilon, we can't assume that this is equal to sigma square. So, this pattern also violate this assumption. Well, and this type of pattern often occurs when Y is a proportion, the response variable is a proportion and Y lies between 0 to 1. Okay, so, this is in this type of situations we often get double bow pattern. Okay. Now, the last one is that the figure D shows the nonlinear pattern. Here this nonlinear pattern indicates that other regressor variables are needed in the model. So, this indicates that the relationship between Y and the regressor variable is not linear, we need to introduce some nonlinear term, and that means consider extra term like square term x square. I mean the relation is not just the linear relation like y equal to beta naught plus beta 1 x. You need to introduce some square term, the higher order term, or you you take a transformation of the response variable y. Okay. I mean maybe we will talk regarding these issues later on again, but what this nonlinear pattern indicates that the relationship between the response variable and the regressor variable is not linear. We need to introduce some other terms like other regressors. For example, you need to take may need to take x square or x cube in the model, or you may need to take a transformation of the response variable y like log y or something 1 by y, something like that. Okay. Now, there is a question you might be wondering, what we did is that we have just checked about the plot of EI against yi hat. So why it is why plotting EI against yi hat, why not EI against yi? So, this is the question, why do we plot the residual EI against yi hat and not against yi for the usual linear model. Okay. It is not so easy to answer this question, like you can think of it EI yi hat. The answer to this question is that EI and yi, we do not consider the plot EI against yi because these two are usually correlated. What I mean by this? Okay, I will talk about that. Whereas EI and yi hat are not correlated. There is no relationship between EI and yi hat. What we are going to prove is that there is a linear relationship between EI and yi. Suppose the relationship is, the form of the relation is EI, I said linear relationship, EI equal to some beta naught plus beta 1 yi plus epsilon I. I mean just a simple linear regression between simple linear relationship between the residual and the observed value yi. Okay. Now, if you know the same technique, this is nothing but the simple linear regression model between the residual and yi. You can check that beta 1 hat is nothing but S EY by S YY. Okay. So, what is ESY? This is the least square estimate. You can check with my first module, beta 1 hat is nothing but this one. This is called the least square estimate. So, this one is nothing but, this is notation only, this is nothing but EI minus E bar into yi minus y bar by summation yi minus y bar whole square. So, what I am trying to prove that there is a relationship between between yi and ei, uh, and I am trying to find out that relationship, what type of relationship they have. If it is linear, then what is the value of the coefficient? Okay. So, this one is nothing but summation E I y I minus y bar. You can check that, it is not difficult, and this one is nothing but the SST. Okay. And again, you know, y bar into E I, that is sum over E I, is going to be 0. So, this is equal to summation E I y I by SST, very simple. Now, in matrix notation, this can be written as E prime y or y prime E, the same thing, okay, by SST. Now, what is E in terms of H notation? Y prime and E, we know E is I minus H y, right, by SST. And we know that, you know, I minus, since H is an idempotent matrix, I minus H is also idempotent matrix. So, I minus H can be replaced by I minus H square. So, this is equal to y prime I minus H into I minus H, because I minus H into I minus H equal to I minus H, as I minus H is an idempotent matrix, into y by SST. Well, so this is nothing but, see, this is E, this is E prime, this is by E prime E by SST. So, E prime E is nothing but SS residual, right. This is nothing but SS residual by SST, which is nothing but 1 minus SS regression by SST, which is nothing but 1 minus R square. So, this R square is the, if you can recall, R square is the coefficient of multiple determination. Well, so the relationship between, what we proved is that there is a linear relationship between the residual and the observed value, and the coefficient value, I mean the slope is equal to, 1 minus R square. Well, let me check with y I hat whether there is a linear relationship between E I and y I hat. We can prove that there is the slope is 0 in that case. So, let me check with E I and y I hat. So, E I, suppose there is a linear relation between E I and y I hat, and the relation is E I equal to beta naught plus beta 1 y I hat plus epsilon, like that, simple linear regression. And then by least square estimate, we can check that beta hat is equal to S E y hat by S y hat y hat. I do not care about this denominator. Let me proceed with S S E y hat. If I can prove that this is equal to 0, then my slope is going to be equal to 0. That means there is no linear relationship between E I and y I hat. So, this is going to be equal to E I minus E bar into y I hat minus y bar. and you can check that this is nothing but summation E I y I hat. So, in matrix notation this is equal to E prime y hat right. So, what is E prime? E prime is equal to y prime 1 minus h, right, because E equal to 1 minus h y, and y hat is equal to h y. We know that y hat is equal to h y. So, h y here. Now, y prime h minus h square into y. Now, see h is an idempotent matrix. So, h square is going to be equal to h. So, this is y prime 0 basically y. So, this is going to be equal to 0. So, there is no so this proves that there is no linear relationship between between the residual and the fitted values. Well, so what I want to conclude here is that unless in case of E I and y I, we have observed that beta 1 hat is equal to 1 minus r square. So, in the case of E I and y I, beta 1 hat is equal to 1 minus r square. Okay. So, unless r square is equal to 1, there is a positive slope, right. There will be a slope of 1 minus r square in E I versus y I plot. Even if there is nothing wrong with the model. So, if you can recall that in E I versus in E I against y I hat plot, I said that if all the residuals are contained in a horizontal band centered around E equal to 0, then the corresponding fitted model is perfect. But here, since there is a theoretical relationship between the residual and the residual and y I, it is very likely that the residuals will not be contained within a horizontal band centered at E equal to 0. There will be a slope of 1 minus r square when r square is not equal to 0. So, that is why it is very difficult to conclude anything if we plot the residual against y I instead of plotting the residual against y I hat. So, that is why the reason and since there is no relationship between E I and y I hat, they are not correlated, there is no linear relationship between them. That is why we prefer plotting the residual against y I hat. Yeah. So, that is all for today. Thank you.